Quick introduction to myself, and I'll introduce our speaker for the day. My name's Austin Claybrook. I joined AGI earlier this year as a corporate system engineer. My primary background is in aerospace engineering. I got my BS in 2016, and I'm currently finishing up my master's in aerospace engineering from the Georgia Institute of Technology. And as the webinar goes on today, I'll be answering any questions, so if you have any, please send them in, and I'll be on the line. And we'll have a few at the end as well. So our primary speaker for today is Doug Cather. Doug serves as the Space Operations Technical Director for AGI. He brings more than 35 years of experience in all phases of space operations, mission design and analysis, and application development. Doug spent more than 25 years with TRW in Northrop Grumman, where he worked on various civil, DoD, and IC space missions. He was also among the first in the industry to start completely automating daily orbital operations during the late 1980s and early 90s. And since then, he's been the primary architect of more than 3 generations of automated orbital operations. Doug also spent 4 years with Rincon Research Corporation, where he performed non-cooperative orbit determination, RFI geolocation, and he holds several patents related to those works with non-cooperative maneuver detection and characterization. Doug also has extensive experience in trajectory, station keeping, both planning and execution, and he has operations experience with launch, early orbit, routine mission, end of life, and special mission operations. So now we're going to go over the agenda for today. We'll go through a quick background of some of the problems and kind of the background of relative motion. We'll go over some of the analytic methods used and maybe some of those problems with not using full force model integration. Then we'll go over the types and some importance of different relative orbits and maneuvers, and then we'll wrap up with questions. So with that, I'll hand it off to Doug, and if you have any questions, please send them in.
Hello, everybody. This is Doug, and I'm happy to be here. It's always fun to be able to share some of this with you. I'm hoping, as a sound check, everybody's able to hear me. Is that true? I hope. Anyhow, on this first intro slide, I have a prox op where I spelled out a nice message for my target satellite, and it's a set of waypoints that we're using to spell out this message of our actual satellite relative trajectory. And my next poll question, which Margaret's going to talk about.
Our next poll question is, approximately how much delta V do you think this proximity operation requires? Please select 1. Less than 2 meters per second, 2 through 10 meters per second, 10 through 50 meters per second, or 50 through 200 meters per second, or more than 200 meters per second. I will give you guys a few more seconds to answer that. Awesome, thank you. It looks like our top result was 28%, less than 2 meters per second.
Well, that is the correct answer. It took just about 1.7 meters per second to perform that relative prox ops. I did spread it out over 2 revs of the orbit. So it's a relatively cheap thing to do from a delta V standpoint, these types of prox ops missions. So that was the point. Now, after showing that hello to my boss here at AGI, he asked me to put it into another language. Unfortunately, I really don't know many other languages, so I put it in my native tongue, and that's what you should see now. So in my native tongue, I spelled it out for my target satellite. At any rate, I didn't know any other foreign languages, so there you go. All right, a little background here. I'm going to talk just a few minutes about the physics of prox ops and the various methods that are out there in implementing prox ops tools and prox ops planning. So one predominant method used today, widely used for proximity operations, is the Hills equations, or some people refer to them as the Closey-Wilshire equations, or even the Hills-Closey-Wilshire, the HCW equations. These are have some significant limitations. I'm not going to discuss in detail about these equations, but they're relatively simple to implement and get a feel for most proximity operations. The limitations are they are linearized, they're for circular orbits only, and the basic ones that I just shared there have nothing but two-body Keplerian propagation involved. There are other versions of them around which include J2 or other higher order zonals, but they still generally you don't see them with other perturbations included. So there is some limitations there. I've included a couple of references on the bottom of this chart for some very good comparisons of various methods and their accuracies for implementation in ProxOps planning. I'm a particular fan of this called the LTT, Lavelle, Tragesser, and Tullifson. They transformed the Closey-Wilshire equations, and you can see on the right there the reformulated set of equations, which now it makes it easy to see the obvious 2-to-1 circumnav nature where X, Y, and Z is radial, in-track, and cross-track. You can see the obvious radial is half of magnitude of the in-track, and that Z is essentially an independent axis. So a couple of good gut feel things to know about ProxOps from these equations and how we get the natural motion circumnav kind of inherently just from this reformulation of the Hills equations. So just a quick look at how that looks when you start applying it compared to full force models. So I've compared here 12 different orbits and how the Hills equations propagation compares to full force model. And you can see for circular orbits that aren't affected by drag, it's not overly significant in the short term if the force models are matched, of course, here in this case. But you can see, as in case 4 there, you can see that this guy had an eccentricity of 0.15 and how horrible the different propagation was. 24 kilometers 24 kilometers per day of propagation difference. So it really falls apart once you add any eccentricity. You can see in the HEO one here on line 8 was nearly 65 kilometers in a day variation. But at GEO and circular, you can see how it was only 3.6 meters a day of differential propagation ephemeris difference. So the moral here is, in general, there's a fair number of reasons to go to full numerical propagation. One of the major ones is differential force models. When you have a prox mission that may have a vastly different area to mass ratio or coefficient of drag or coefficient of reflectivity, then the differential force model is significant, and that is generally not accounted for in these simpler methods. So full numeric propagation is generally required in planning a real mission, especially when the satellites are not matched. So let me then take that from that brief physics background, go into real rapidly a little bit about rendezvous. Rendezvous, there are many types of rendezvous performed. So this is the piece where you're moving towards your target, but before you have started necessarily making your proximity operation close-in maneuvers. So in rendezvous, the minimum delta V is a common rendezvous transfer where you find a minimum delta V given your constraints of transfer time or start and stop times. There is a solution that yields the minimum delta V. In the GEO-to-GEO, for example, geosynchronous to geosynchronous orbits, a lot of people rendezvous via drifting above or below the geobelt circular, and then coming back and rendezvousing with the target satellite at the geo altitude when their longitude is nearly matched. There's many other types of rendezvous where they plane match first, followed by other orbital parameters, the eccentricity vector, semi-major axis matching, and then finally, once the orbits match, they will then use a drifting phase, which just varies the semi-major axis until it matches, very akin to the GEO-to-GEO transfer. So in this picture, you can see there are, I have two different rendezvous represented here. The red one that you see is the minimum delta V transfer, and many GEO operators would find this offensive in that each rev, this was a 5 rev transfer, each rev, you can see it dropping down onto the GEO belt and probably insulting a few of the other residents there with a conjunction message. So it's generally not neighbor friendly to perform that type of transfer, but it was the minimum delta V rendezvous for this solution. Now in this yellow case, that is the one where we drifted from the chase satellite, which is on the far right, over to the target satellite in the middle of the screen there. You can see how we drifted to the west, so we went above the GEO belt, and before we descended at the right time to rendezvous with our desired satellite. So that's a common form. Here's a LEO to MEO type rendezvous, where we have the one LEO orbit there in magenta, and the RPO satellite labeled doing a transfer, and you can see it's going to rendezvous with that target there where those two orbits intersect. So many types of rendezvous situations, and these were just a couple of simple examples. One of the things I'll show you a little bit about a Astrogator sequence, the tool I was using to do these, which I'll talk more about at the end of this hour. This is an Astrogator sequence that shows and walks through those steps to do that GEO-to-GEO friendly transfer, not the optimal, but it's starting drift rates and matching planes, and then coming back and performing the final stage rendezvous. So we'll look some more at these towards the end of this segment. In this particular Astrogator screenshot, I'm showing a very handy feature of plane matching. How do you match a plane? When do you match the orbital plane of another target satellite? And there's a really nice feature here which lets you propagate to an ascending node, but which ascending node? I used the target satellite's radial intract cross-track axes, and when I intersect the ascending node of the target satellite's radial intract plane, then that is the perfect time when those the common line of nodes of these two orbits, and then so that makes matching planes quite simple to do in Astrogator. So just a side note there. Now I'm going to move into various relative orbits and types of relative orbits, and there's a slew of these to get through. We'll go through them relatively quickly. What is a relative orbit? They're orbits which appear to follow certain relative paths around a target satellite. I classify them in two subcategories. There's natural motion, there is forced motion. Natural motion meaning I'm using the predefined physics, such as the Hills equations or regular propagation, not requiring delta V in order to keep these relative orbits stable. The only difference there is differential force models. If you have a vastly different drag or solar radiation pressure parameter, then there will be a modest amount of station keeping required, albeit quite small and somewhat infrequent. And the station keeping can be done several ways to affect station keeping. It can be through the use of thrusters. It can be done through like off-pointing your attitude, or off-pointing solar panels in order to get the desired station-keeping effect for natural motion. When it comes to force motion, there are frequent delta V's required, sometimes not as frequent as others, sometimes fairly frequent to maintain a relative orbit. So I classify natural motion subpieces is sitting on the V-bar for natural motion, or the natural motion circumnav as shown by those LTT equations. Then there's things like what I call spiral flyby. In force motion, the subcategories are many. You can virtually have a limitless amount of force motion relative orbits. Some common ones that you'll hear talked about in the industry: teardrops, force motion circumnavs, a perch point, follow sun, a hop, waypoint following. Waypoints was example of the hello diagram. So that followed a series of waypoints. So let's get in and take a look at a few of these. The VBar offset is a stable relative orbit, requires little or no delta V. It's one where the prox satellite is sitting on the velocity vector or the anti-velocity vector of the target satellite. This is a fairly, all the other orbital conditions are matched. It's just at a slightly different position in true anomaly, for example, along that arc. So it appears to just sit there and hang out at that constant distance. And it's effectively a special circumstance of a perch point where you maintain a single spot relative to the target satellite. This is a very common prox-ops event where you just sit close. It doesn't require much delta V to stay there, only requiring station keeping to overcome differential force models. And of course, the further away it is from the target, the more there is of that to do as well, because the differential force models in gravity and solar, lunar, and other things start to be larger. There is some risk in sitting too close in the in-track direction to the target, because if the target performs any type of in-track maneuver, you are at risk of conjunction with that guy. So let's go ahead and take a look at that picture. The VBar offset orbit looks like this. You can see my radial in-track, cross-track axes denoted there. So X, Y, and Z is radial, in-track, and cross-track. So along the plus in-track is the RIC y-axis denoted, and the VBar offset, in this case, I am sitting in the negative velocity direction, or to the west, as I denoted, of the target. And that's a stable point, and it can stay there for quite some time. Let's look a little bit at an Astrogator panel. How does it look like for that sequence? So I'll just introduce something additional with Astrogator. There's a scripting tool, as you can see. You can see up here, I've enabled a scripting tool, and I've given it several parameters. So this way, a user of Astrogator can say, oh, I want to find the condition for a VBar offset of +1 kilometer, for example. All you do is type that in and rerun the sequence, and now that will change it out to do that. So user parameters are a useful concept for an Astrogator scenario here. So that's a typical panel for a prox-ops instance in Astrogator. Let me look and take one more look at this initial state. Defining the initial state, there's a clever little trick here where I define the coordinate system. The coordinate system that I'm defining my initial state in is against the target. This is my chase vehicle, but I want to define the coordinate system of the target relative to the target. So in its radial in-track and cross-track axes of the target, what is my initial condition? So for a VBar offset, I can set that Y component to like whatever, -1 kilometer, -300 meters, whatever I like, and have that be my initial guess for the exact condition to maintain this VBar offset. So another very useful concept is the initial coordinate system and flexibility there to define these in. So let's take a look at a natural motion circumnav next. The natural motion circumnav is, again, a stable orbit requiring little or no delta V. as long as the force models are matched pretty well. And if they're not, it just takes a very modest and somewhat infrequent delta V or off pointing in order to keep it there. This is one where you get to survey pretty much the entire target. It has the 2-to-1 equation. The radial distance is half the in-track distance in maximum excursion around the target. And you can have any cross-track components, more or less, that you desire here. So it has a 3-dimensional feeling as well. Here's a picture of the natural motion Circumnav, where you can see, in this case, it's totally in plane. So in the in-track direction, you see twice the distance of that semi-minor axis, which is in the radial direction. And that, again, is a relatively stable. It moves around once per rev of the target. Here is a case in this slide where you can see I've offset it in multiple axes. It never crosses the in-track axis, it never crosses the radial axis, and it never crosses the cross-track axis itself. It is considered a much more of a safety ellipse. That is a term coined by some in the industry of a natural motion circumnav like this, so that if the target satellite performs any of those cardinal maneuvers, then it would not collide or conjunct with the relative orbit there. All right, so another type of passive relative orbit is what I call the flyby relative orbits. These are one where the chase satellite performs kind of a passive flyby. So it doesn't stay there, it doesn't remain in a proxops, but it performs one as it goes by, and it can go by quite slowly or fast to perform a safe and passive inspection. So there are types of relative orbits. I'll just name a few: the encompassing spiral, the flat drift. I'll give you a picture. Here's what I call the corkscrew. So I know that you attended this webinar if you call this the corkscrew out in public again. So this is a term that I've coined. I call this the corkscrew relative orbit. You can see how it just kind of spirals around the target satellite as it passes by, and then it will keep drifting relative to it with each spiral rev as it goes by. Here's one where it just is swinging by on top. In this case, you could do it below. I call this the flat drifting flyby. So all kinds of these conditions, you can dream up many types of drifting by relative orbits too, where you don't perform any maneuvers or any station keeping while it's in the middle of it, but you can wait till you've drifted past it to exit the scene. So let's look at some force motion ones next. The first one I'll bring up is the so-called industry so-called teardrop. It is not a stable orbit. It does require delta V's to maintain it. It's one where the proximity op satellite operates generally along the radial direction, either positive or negative, and maintains a teardrop-looking relative orbit. You can also encompass the satellite. Those are called encompassing teardrops as well. So you can be on top or below, or you can actually encompass as you go around your teardrop, your target satellite. So let's take a look at a basic one of these. This is why it's called the teardrop. It very much looks like a teardrop. In this case, under it, it's a mirror image of that if you were on top of it. And the maneuver in this case is performed at the very bottom. You see the sharp edge right down here. If I can move my mouse there. Here we are. If you can see the sharp edge there in the teardrop, and that's where a radial maneuver is required to maintain this teardrop every time it comes around. There are several uses for teardrops in missions, but in this case, this maneuver is done down here at the teardrop. If it were on top of the satellite, that would be done obviously at the top. This is mirror imaged, and it's the other direction. But the radial, it's a pure radial maneuver required in this case at each one of those. And it's a relatively cheap one to maintain. In this case, I'm showing you how much delta V that took to maintain for 24 hours. This is a GEO satellite target. And in this case, it took 4 maneuvers throughout that 24 hours, and it cost just 25 centimeters a second to perform that maneuver for an entire rev. So again, not too costly and not all that frequent is required, since you only had to do one here about every 7.5 hours or so. All right, so let's look. Here is the encompassing teardrop. So this is where I've come in on the top. You can see the turnaround point over here is up at the top, but I encompass the target satellite as I go around the teardrop. Again, a relatively simple relative orbit to design and perform. The next relative orbit I'm going to look at is the forced motion circumnav. In the forced motion circumnav, it is not a stable one. What we're trying to do in this case is keep a perfect circle, not a 2-to-1 ellipse, around the target. So we want to keep a constant distance from the target in general as we go around this special forced motion circumnav. So here is what that looks like. You can see it took many maneuvers. In this case, I divided the orbit into 36 pieces. I performed a maneuver virtually every 10 degrees of true anomaly to keep that looking like a circle. The total delta V for this, again, was well under 2 meters a second. And in some cases, it just depends on the size and the relative location. Now, I don't have to keep this target in the middle of my circle. I can perform the circle, I can offset it, and then I can orient it in any axis. So here's another special condition where I've put in what I call the halo orbit. The target is under me, and nadir is underneath there. You can see where the radial axis is in that arrow pointing up here, the green one. So I simply oriented the force motion circumnav to be offset in the radial axis and to be in the in-track, cross-track plane. And that essentially performs a halo type orbit. So now you can begin to see the kind of limitless possibilities for a force motion circumnav where you rotate this in any axis, any number of degrees. I can put it 45 degrees to any axis, 30 degrees, anywhere you want, and have a rather interesting relative orbit in a forced motion circumnav. You can choose to do fewer maneuvers per rev and not follow as true of a circle, or many other options are available in this one. But again, it's a relatively inexpensive from a ProxOps mission standpoint relative orbit to maintain. So the next one I'm looking at is a perch point. In a perch point, it's not a stable orbit, so it requires more delta Vs. It's one where you want to keep a constant relative position in all 3 axes relative to the target. So people call this a hover sometimes. There are many different names. I refer to it as a perch. In this perch, you can see in this picture how that point of the perch satellite is maintained. That is not stable. Remember, we discussed earlier, the only stable perch point would be on the VBar axis, on the velocity direction. But in this case, it's not along the VBar, so it takes frequent delta Vs to maintain. Now, what does a perch look like there? What does it look like? In here, I've zoomed in on the actual perch point, and that circle here where I've encompassed the perch point is just 1 meter. I was holding this 200 meters off of the target, and I allowed it just 1 meter of variation. So you can see it's essentially a teardrop being performed 3-dimensionally with the maneuvers to maintain it down here at the bottom, telling it to shoot to the other end of my maximum allowed error. In this case, it was 1 meter, until it comes back and perform that. And so you can see in this 1 day, 24-hour period, it took about a dozen of these to maintain it. So let's look at the hop. The hop is a way to go from one relative like perch point to another, or one position to another relative to the target. And there are many ways to do hops. Some want to go in a straight line. Some want to find the minimum delta V solution. So that means you're allowed to vary the time of flight between those 2 points in order to find the minimum delta V. Sometimes a hop is a constrained time of flight. Just give me the minimum delta V given this time of flight kind of thing. Others, like I said, want a straight line. Follow a straight line. That takes more maneuvers along the way. It's just not the start and the stop. So in this case, I'm going to show you there was just the 2 maneuvers. I was sitting on the V-bar, and I'm hopping to a perch point, and there it will be stopped and maintained actively at a perch point. So this one used, for an example, a minimum delta V solution. So this found the optimum time of flight in order to make this hop. Now, from a hop, a very specific version of an optimal hop is called the VBar Hop, where you move from one position on the V-bar to another. It is 2 radial maneuvers. You start it with a radial maneuver and you stop it with the opposite radial maneuver. If you fail to do the second maneuver, all you've done is initiated a circumnav. You can see that lower half here, as I'm transferring from this position here over to the far right, from the left to the right, it goes underneath, because when you go underneath, you move to the east. And in this case, I was hopping from one relative position to another, and 2 radial maneuvers. It's a very specific instance of a hop, and it's a optimal hop, but it takes half a rev. It always is a half a rev solution. So the time of flight to be most efficient is exactly half a rev. Let's look at the follow sun relative orbit. In the follow sun relative orbit, I am trying to put the chase satellite in between the target and the sun. So that gives him good sunlighting on the target, so the chase satellite can see the target quite well and be able to track it just fine should he have his closed loop control system. So that kind of looks like this. You can see in this case, it is offset in the cross-track direction. This is a GEO bird again, and so at this time of year, the sun was in the northern hemisphere, so it was offset in the +Z direction, so it follows the sun. This point here of the sun, it's always halfway, it's always not halfway, it's always in between the sun and the target, and providing good, good visibility with lighting. And you can split this into as many, again, tiny little hops from one point to the next to maintain that. Again, this total 1 rev delta V was under 2 meters a second to maintain that whole relative orbit. So force motion waypoints. We looked at the example right up front. Slide 1 was the hello. That's a force motion waypoint. That's where you follow a path moving from one position to another and holding at a position if desired. This is a different example of a force motion. So we want to take a specific path around the target, and it follows that in a prescribed time using straight lines in this case. So I added a little bit of logic here that says follow a straight line from one point to the next. That way it's kind of easier to guarantee you're not going to have conjunction. If you are looking for optimal delta V minimization schemes, for example, you have to go to a little extra worry about am I going to conjunct with my target in the middle of that. Now to just switch gears a little bit, application to formation flying. So what is formation flying? There are many conceived formation flying missions now. Many use VBar offsets and or natural motion circumnavs about another object or even an empty point in space. For ease of operations, most people match these satellites. They look alike. They have similar SRP or drag modeling, so you don't have to worry about the differential forces too much building up on you and having to do much more frequent delta Vs. So Many different missions are being proposed under formation flying. You can form large apertures or antennas or synthetic aperture radars or whatever. There's many different missions out there proposed. So what does that look like? Here's a formation where I've removed a bunch of them out of the picture, but you can see in the green orbits, those are all the same size. The yellow is another size and the red is another. They are all using the 2-to-1 natural motion circumnav, but they have varying cross-track components to affect different orbital, essentially relative orbital planes. I like to think of it as like a relative inclination in RAN. Here, it's not quite that, but that's one way of pondering it, is you're looking at different planes of relative motion, and by using that cross-track component to separate them like this. So if you take a little look, or a little closer look, excuse me, you'll see the inner one, all those green ones. I left all of them on from this thing. They are all the same circumnav. So looking down this thing at the in-track and radial axes only, looking down the cross-track plane, so now you can't see any cross-track components, you can see how they are just 3 different sizes of natural motions. So a fairly common way to fly formations, in addition adding VBar offsets in there as well, because these will be somewhat optimal for formation, since very little delta V is required to maintain them if they're essentially if the objects are matched, like in they're similar spacecraft bodies. So the delta force models are very similar. So ProxOps also is quite applicable here then to this formation flying. Now, I'm going to switch gears a little bit before we're done, and give you a quick Astrogator overview, a little bit about what Astrogator is. Astrogator is the tool I use to do all these analyses and to produce all these orbits and full ProxOps missions, including, all-in-one satellite, putting together, the rendezvous with various different ProxOps, and finally the exit strategy to leave. So Astrogator is able to put the whole mission together. Astrogator is a maneuver planning tool, trajectory design tool. It has a high fidelity numerical satellite propagator in it. It has virtually any option you would want, plus plug-in points for force models that you want to add to. It has trajectory optimization pieces. There's differential correctors, and in addition to optimizers, SNOpt and IPOpt, 2 rather well-known industry standards in the optimization scheme as well. So it's been used for many different purposes, from launch planning, station keeping, interplanetary. It's been used just about for many different types, and including in ops, in mission planning, end-of-life maneuvers, station changes, infrequent maneuvers. So it has quite a lot of heritage in it, and quite a lot of users. So I'm going to look at quickly through the Astrogator interface. In the interface, you can see here, I've just highlighted the mission control sequence. This is the piece where it's a graphical, essentially a graphical coding language, where I'm telling it, here are the stages of my orbit. Here's a launch segment that's highlighted here, coasting, maneuvers, propagators, all these things. So you put together the logic here, and it will execute this sequence. So in here, there's a targeter and an optimizer wrapped around this as well. So you target certain parameters, and then you can optimize those parameters, and they can be nested like that. So let's look at the segment properties. In this case, a launch sequence was highlighted. You can see how to define parameters. Where was the launch? How was it burn out? Spacecraft parameters such as dry mass, areas for solar radiation pressure and drag, and those types of things. Fuel tank, how much fuel is in it, and other user-defined variables are allowed to be in there as well. In the MCS toolbar, a series of menu items, essentially of things you can do inside Astrogator. Down here, segment results. For example, when you're in a targeter, you want to have a result. So the result of, for example, this propagate segment might be an altitude. So I want to target the delta V to achieve a certain altitude. So you define down here the results of a given segment inside the MCS to be a certain parameter. So what is the result you're looking for to get? Down here is the segment boundary times. So those are when does this segment start and stop? And you can highlight the entire optimizer. For example, it'll tell you when that whole thing, all the segments underneath that optimizer started and stopped. So you get those properties. There is a component browser. And in here, there are just virtually unlimited amount of things you can define as for results or targeting or stopping conditions. There are propagators you can define. You can define engines and thruster sets and all those various things that Astrogator you may want to use in your Astrogator run. So this is, I mean, there's literally 50,000 things you could do here and then make your own. There's a set of built-in ones. You can see over here, if it's green, it means that the user added it. It's editable. The yellow or orangish color is ones that are default. You can copy and paste them and then edit them, but those are the ones built in when Astrogator is set up. So MCS segments, there are two types of MCS segments. Remember on the previous page, we were looking at various segments, a propagate, a maneuver, a target segments. So they make up an MCS. There are two types of segments. There's ones that actually generate ephemeris and ones that actually affect the execution. So in there you can see various types of ones that generate ephemeris, and you have sequences, target sequences, optimizers that affect the MCS sequence, but don't generate ephemeris themselves. It's the segments inside them that generate the ephemeris. So Astrogator essentially is a graphical programming language that lets you set up various things. Do whiles, you can think of it, maybe I'm old-fashioned with my Fortran background, so do whiles and if-thens and logicals and ors and logical ands and subroutines. So I've kind of drawn a kind of a parallel here. An auto sequence is like a subroutine. Stopping conditions are logically anded, whereas stopping condition constraints are logically anded, whereas the stopping conditions themselves are ORed when you get to things. So so there's tons of possibilities there. Now I'm going to talk about one of my last pieces, which is a note about proximity ops and orbit determination. Orbit determination is really critical for any prox mission. Knowing your relative positions is an actual safety issue, and having that known accurately is really critical. Inside our ODTK at AGI, we use a real-time common filter. This can process multiple satellites in a single run, which is really handy when you can also process these relative measurements. Relative measurements are critical in prox ops, for especially close-in prox ops. If you want to do, 10-meter inspections, you really need to know your positions, your relative positions. At that point, absolute positions in Earth-centered inertial is not important. It's how accurate do you know your relative positions to each other? If they're both off a kilometer in the exact same direction, nobody really cares for the prox op. What matters here is the relative position. So relative measurements such as space-based angles or range or ground-based telescope data with relative measurements of delta right ascension, for example, or delta declination, those are really useful to process when looking at a prox mission. So it provides for a very accurate relative uncertainty, which is really key to successful prox ops. Astrogator and ODTK share maneuver and thruster information. So another key piece for operations is the ability for your OD tool and your mission planning tool for prox ops to share this information and to go back and forth for calibration, for planning. So there's pre-event and post-event interaction that's really required for a successful proximity operation. So I think next we're just going to go into back to Margaret.
So our first question from the audience is, how can I get trained on these tools?
Hi, Maggie. I think I'll answer that one. I'll leave the others to Doug. So if anyone's interested in further training related to Astrogator, ODTK, or anything we kind of covered today, on our website at agi.com/training, the link will be in the slide after this. You can find our training tabs, or you can go through our level 1, level 2, and level 3 certifications, which cover a broad scope of things, everything from STK free to coverage to comms to Astrogator. Towards the level 3 and level 2, we have some more specific tutorials. You can also find those at help.agi.com. We also offer training classes. So if you or your organization are interested in learning more about these specifically, we offer 2 or 3 day Astrogator training classes where we'll come in and have an engineer come and present to you. We also offer a 3-day relative motion and prox ops class. So a lot of the material we covered here over 3 days presented to your company. We also have a 3-day ODTK training class. And if you're interested in that and you're already working with us, you can contact your account representative, or you can email info@agi.com. And once again, that'll be on the slide after this.
Awesome. Thanks, Austin. And our second question from the audience is, why is this important and who does this impact?
All right, Austin, did you want me to handle that?
Yeah, if you want to take those, and we'll have a few more to pass your way too.
Well, there's several reasons why prox ops is important. One, I mean, obviously there's the obvious cooperative piece where you're doing a survey, you're looking at a satellite, it has damage, you want to survey a satellite. Two, for example, the space station, when you bring in supplies, it has to do a prox ops mission and dock. So resupply mission, or you can even think of a refueling mission, for example, is another key piece for prox ops. From a potential space threat standpoint, is somebody, we've detected somebody near me, what might be their motion, relative motion to me, what might be their future behavior. If I've detected they've gone into a teardrop, when's the next move? How can I assess that? So there's various reasons there to care about prox ops.
Awesome. And another is, what type of force, motion, relative orbits have been used in practice?
What type of force motion? Well, mostly to date, I've been associated with like waypoints. So people will define relative waypoints. But at NASA, they love the VBar Hop. They love the VBar approach. I didn't talk about that today. VBar approach and R-bar approach, where you ride up those lines. So it's you're instead of hopping and having that excursion like I showed, they're kind of sticking very close to that cardinal axis and coming right up the VBar or the R-bar. The R-bar approach is considered a relatively safe approach for docking purposes, because if the satellite loses communication with the proxying satellite, if the ground loses communication with the proxying satellite and the commands fail to go out to keep maneuvering, it naturally drifts away from the target. So R-bar, although not nearly as cheap as a VBar approach, is safer, because if you fail to keep communication, it naturally drifts away from your target. So that one is a common one in use at NASA.
Awesome. Thanks, Doug. And last but not least, at what distance from the target do you define prox ops?
Oh, that's a great question. So I have several definitions. I think prox ops are when you're within less than 100 kilometers. Close-in prox ops I define when you're below a kilometer, and the rest of those are kind of like far. 1 to 10 kilometers like medium, 10 to 100 is like a large prox. I use the term formation as another side point for these types of distances. I use the word constellation when someone is having satellites much further than that distance, or even think of like the Walker constellation or Flower constellations, whereas a formation is one where they're operating very close proximity like this. So all kinds of prox ops at those distances have been demonstrated in the past via various owners and operators and governments and various people, but it takes a gutsier person to want to get within 10 meters or so of a satellite that means you need onboard controlling essentially that takes over and is quite active during that time. It's very difficult to perform that close in without automated navigation.
Great. And we are actually going to answer a few more since we have some time. Can one determine the probability mission of an unknown chaser by the type of RPO the threat space object used?
So the question was, can we determine its intent?
Yes.
How would you characterize that?
Yes.
So that's difficult to say. There are some, if you detect these in a certain specific type of relative orbit, there are some that are more suited for things than others. So if someone were to perch at a certain distance from your solar panels, that would be of interest. If someone were to perch between you and the sun to blot out your sun sensor or a specific star sensor, that would have interesting intent. But if they were coming in on the R bar, it seems like their intent is to possibly dock or something like that. It is possible there are certain relative orbits that are better suited for certain mission intents. Yes, and mostly, I mean, if you see somebody doing a spiral, that to me shows intent to survey. They want to get a good look at you from all angles and various sun angles and sun phases. So that to me, signals intent to survey. Now, other than that, I mean, there's all kinds of other intentions, but you can't, definitively associate them with a given intent.
Great. And now this is definitely the last question.
Okay.
How close is too close information flying applications?
How close is too close? Well, you definitely don't want to have a conjunction, right? So conjunctions are frowned upon, and pieces falling off would really hurt your whole effort. So I tend to say you'd want to operate at least 50 meters from your target in general to have some safety, and that requires some, very precise maneuvering there. The people that I know of today doing these are typically staying more than about 500 meters away to perform their mission, and that gives them good safety. At least the ones we've watched at the Comstock. We've watched certain prox missions, and we don't see many people trying to go below that distance. So safety is always a matter of the sensors you have on board and the navigation system you have, and your confidence in your system, the fine thruster control, and those kinds of things. So I would say you could effectively operate very close with very fine equipment. With coarse equipment, you need more and more. But as you get closer, the orbit determination requirements go up in addition to your navigation requirements. So it's also a money trade-off there as well.
Great. Thanks so much, Doug. And to wrap up, the products we mentioned today are Astrogator and ODTK. If you want to learn more, you can check out agi.com/training for some basic STK training. You can talk to an engineer by emailing info@agi.com. And you can look for future webinars at agi.com/blogs. Thanks for joining the webinar. For those questions we didn't get to, we will be answering those individually after we sign off. We will also send each of you an email with a link to view this webinar again. Make sure to check out our next webinar hosted by special guest Sam Gilbert on July 26th. He will give us a user's perspective on customizing trajectory design tools. Registration is now live at agi.com under the Events tab. See you next time.